Lab session number 5 statement to verify by simulating in essay the results of the analytical formula for the stiffness of beams in series combination and different types of loadings. So in this lab session, we will actually be taking this example number 1.7 from the textbook of mechanical vibration by SS Roy, equivalent K of the string drum. So in this lab session, we will actually be modeling a combination of beams which are connected in series. So first is the cantilever beam having length B and its thickness is T. So and on its free end there is mounted a Huston drum around which a steel wire rope is wrapped, and one end of the this wire rope, this steel wire rope having length L is suspended from the Huston drum, and the diameter of this wire is D, and on its lower end, lower free end, there is a weight W suspended. And we also know that this load suspended is actually works as the initial excitation for the free vibration. So as far as this cantilever beam is concerned, when we will be observing it from the right side, from the right end, so we will be getting its cross section, and the cross section horizontal dimension is A, which is actually the base, and its vertical dimension is the same as this dimension D. So the stiffness formula for the cantilever beam is shown here. We can observe it. So this is the cantilever beam stiffness formula, KB, K subscript B, stiffness for the cantilever beam, which is equal to 3EI over L cube actually, or here length of the beam is denoted by B, so it is B cube. And E is the modulus of velocity, and I is the second area moment of inertia, which is actually BH cube by 12. Here B is equal to A and H is equal to T. So BH cube by 12 comes out to be AT cube by 12. So EAT cube by 4B cube, it is actually the formula for the stiffness of the cantilever beam, and KR, which is actually the stiffness of the wire rope, and it is a beam under tensile loading, a rod under tensile loading, just like the cylinder member rod under tension or compression. So AE by L, and here cross sectional area of the wire rope, which is equal to pi d square by 4, and E is the modulus of elasticity, and L is the length of the suspended wire rope. So these two beams are in series combination, and the formula for series combination for the stiffness, equivalent stiffness, has been applied. So 1 over K equivalent is equal to 1 over KB plus 1 over KR, which is equal to 4B cube by EAT cube plus 4L by pi d square E, and which comes out to be K equivalent is equal to E by 4 pi AT cube by d square and pi d square B cube plus LAT cube. So we will be assuming some parameter and dimensions for the modeling of our beam. So what we will be doing, we will first be modeling these two beams which have been shown here. We will be clearing all this drawing. So We will first of all we will be modeling a cantilever beam. So we have opened the design modeler geometry module, and here we will be making the sketch for the cantilever beam on the XY plane, and on the XY plane we have on the cantilever beam we will be on the XY plane on X-axis we will be creating this cantilever beam, and we will be drawing a horizontal line. Its one end is on origin and it is located on the negative x-axis direction, and its horizontal dimension which is equal to h1 10 meter. And after having drawing the sketch for this 10 meter line, we will be converting this line into a line body. So we will be going on selecting sketch 1, and then we will be clicking on concept menu, line from sketches, and after line from sketches we will be coming on this situation. We will be selecting the line, and here sketch 1 will be selected, and it has add material property, and in this way we will be clicking on generate, and this line body will be created. So the line body for cantilever beam has been created. After that we will be creating the sketch 2 for the suspended wire rope, which is vertically suspended. So we will be clicking on XY plane, and then we will be clicking on this new sketch, and sketch 2 will be added up in the XY tree menu. So then we will be clicking on sketch 2 and we'll go to sketching tab, and sketching tab on y-axis in the negative direction we will be creating this vertical line segment having vertical dimension denoted as V2, which is equal to 10 meter assumed value, and then we will, in a similar manner, we will be converting this line sketch into the line body by going into concept menu, then from line from sketches, and this line 2 will be created. After that we will be adding 2 cross section. We will be going to concept menu cross section. First will be the rectangular cross section, and this rectangular cross section will be added, and the cross section has the dimension assumed as 3 meter and 0.25 meter is its vertical height. And after that we will be adding the circular cross section for the suspended wire rope, and its radius is 0.2 meter. So in this way 2 cross sections will be created. And it is also to note here that when we will be assigning and it is also very important to note here that these 2 line bodies which have been created as line 1 and line 2. So remember that line 2 must be created as add frozen. Here we can observe that line 1 has the setting as add material, but line 2 must be add frozen, because so that individual bodies can be distinguished or created in the ANSYS environment. So line 2 must be created as add frozen, not as add material. So in this way, 2 line bodies have been created. Body, this is for the cantilever beam, and this line body, which is vertically along the negative y-axis, for the steel wire rope. So it is also to note here that when we have applied this rectangular cross section dimension, which is d 3 meter and h is 0.25 meter, and by default the beam, cantilever beam, we can show here in the 3 dimension this way. These 2 bodies have been shown. We can observe that this cantilever beam by default, after assigning the rectangular cross section, this line body, this cross section actually the section of this cantilever beam will be in the vertical direction. So we will have to align it along the horizontal orientation. So the section will be 90 degree rotated about its central line or central axis. So what we will be doing, that the method to rotate a section for the beam, which is actually we will be clicking on the edge filter in this way. For example, this beam is the section is in the B is in the horizontal orientation and T is in the vertical direction. So we have to rotate this complete section of the beam 90 degree in the vertical direction. So what we will be doing, that we will be selecting the edge filter, and from the edge filter we will be clicking on selecting this line, and here initially will be written rotate 0 degree. So here we can observe, if I am putting here 0 degree, and I can observe that the beam will be rotated in the vertical orientation. So initially the beam will look like this when we will be assigning B is equal to 3 meter and H is equal to 0.25 meter. The beam in the initial setup will look like this. We will have to rotate it by typing here 90 degree, and the beam will be rotated, the section of the beam will be rotated 90 degree, and it will be aligned as shown. So the geometry step has been completed. After that, we can close it, or we can leave it as it is, and then we will be clicking on engineering data, and here engineering data has been opened, and in the engineering data we will be creating a density. Assumed we can 10 raised power minus 20 or minus 15, so that both the beams have been made of negligible mass. So we will only be creating default material having density 1e minus 15. That means 10 raised power minus 15 or 10 raised power minus 20. 1e minus 20. So any suitable negligible value of density can be assumed. So after assigning the density, then we will be opening this model cell, which is A4 cell, and when we will be we will have opened the model cell, then we must verify that these two line bodies must have negligible mass, and their negligible mass can be checked by checking their properties, that here its volume is 7.5 and mass is 7.5 10 raised power minus 15, which is negligibly small, very small value. And in the similar manner, line 2 body for the steel wire rope, which is also having very negligible mass. So we will be adding a point mass for the end load W, which is shown here. This is the load W, but as in the model module, there is no gravity, so we can assume the end weight to be as the point mass, and point mass has been just assumed as to be 50 kilogram. So end mass has been applied. After that, the important point to be noted is that we will be creating a revolute joint at this point. We will be creating a revolute joint at this point. So revolute joint, how it will be created? The method to create revolute joint is that we will be, for example, first we will be hiding the vertical line body in this way. Vertical line body will be hidden, and after that we will be clicking on this revolute joint, and in the revolute joint we will have the setting as body dash body, and we will first come on the mobile, and here we will be clicking on the scope, and we will be clicking on this point, and then we will be clicking on apply, and in this way this point will be selected, and after that we will be showing this line body and will be hiding the other line body. So we will be showing this line body, and we will be hiding the first line body. So when we have shown the other line body, then we will again go to the revolute joint, and first we had selected scope in the vertex in the mobile this point, but now we will be moving in the reference section, and we will be clicking on the scope in the reference section. So we will be again be selecting this point, and then we will be applying, and in this way revolute joint will be completed. And we must note that here green tick mark should be clearly visible when the successfully revolute joint has been created or applied. So the important point is that why we hide one line body and then we select the end point, a common point. The reason is that if we do not hide or suppress one line body, then the same point will be selected both times. So the distinct points cannot be selected, because this point is common for both the cantilever beam and the vertical steel wire rope. So this point to clearly indicate or specify that this point is selected at different beams, we must hide one line body or one body at one time, and then we should make it visible for the foolproof selection of the same point on two different bodies. So in this way, Revolute joint will be created, and after that, this name selection is not necessary. We can simply delete it. So this was optional, and the other step which will be important, this is the fixed support, and fixed support will be applied on this vertical line body that we have shown. So the fixed support will be applied at this point. So fixed support will be applied. So after applying the fixed support, this nodal displacement is actually unnecessary. We can delete it. Instead of nodal displacement, we can apply simply displacement, insert displacement, and we can apply the displacement at this point, mass point, and we will be putting it x0 and z0 and y y3. So in this way, analysis setting mode will be 1, and in this way total deformation will be entered, and then we will be proceeding towards its solution, and the solution will be created. Solution is taking time, and when the process of the solution is continued, we must wait patiently so that the solution is not interrupted and successfully solved. So solution has been done, and in this way we can say that in this way, this is the simulation, and its frequency is 34.434, and we can 34.434 hertz, and we can verify this frequency from by hand calculation or manual calculation, that formula for the formula for the frequency in hertz, which is actually small f which is equal to 1 over 2 pi square root of a actually square root of a equivalent by m. So here we must know what will be the value of a equivalent. So the value of a equivalent, which is equal to 2 pi, which is equal to 2, which is equal to 2 pi which is equal to 2 pi f whole square into m. So it comes out to be 2 to be which comes out to be 2 pi and dot 34.34 whole square and multiplied by m, which is 50 kilogram assumed. So this comes out to be, we can calculate it, so stiffness comes out to be 2, 3, 0, 4, 2, 3, 4, 0, 4, 7, 8.69 Newton per